hello everyone. So as mentioned, I'm going to talk to you a little bit about graph processing. And what I wanted to do was to give you an overview of what we have been doing on graph processing, specifically on performance modeling for the last, I think by now there are 8 or 9 years. So we still think this is a difficult nut to crack. Let's see how far we get. But as I said, feel free to interrupt if anything is unclear. So I'm going to start a little bit with the boring stuff. If I can, yes, there we go. So by basically claiming that graph processing is really everywhere, and you really get to see a lot of applications coming from social networks, and that's kind of traditional. But at this point, we've seen applications from bioinformatics, a lot of pandemic analysis, and in general, kind of propagation of information in various types of situations. We have seen very nice applications of fraud detection, and of course, neural networks are also starting to look into graph processing or rely on graph processing. So there is, needless to say, graph processing is an application that is, at least for now, here to stay, and it's only getting more complex. Of course, the purpose of this talk is to really discuss about the performance of graph processing and what happens when graphs and graph processing are basically starting to increase in complexity. So one thing that I want to mention is that we're looking in principle at large-scale graph processing. So we're interested in cases where graphs themselves grow larger, and also graph processing itself as a process or as an algorithm is getting increasingly complex. So the question is, what shall we do when we start seeing that, say, if you're a very basic user of graph processing, you use your network X library and you find out that you need to wait for a few good hours for a basic analysis. So in that case, of course, we argued that you need to have better algorithms and better platforms. And we're going to try to do what we did for many other applications, namely use parallel processing and new parallel platforms, be it CPUs, GPUs, or combinations thereof, to actually improve the performance of graph processing. So arguably, parallelism is the way forward for graph processing as well. But of course, this doesn't come for free, or it doesn't come without challenges. And since already 2007, there's quite a long list of publications that are claiming that graph processing parallelism are not really a good match. So effectively, on the one hand, parallel architecture really rely on massive parallelism, on regular massive parallel processing. They really look for high throughput, and they have significant penalties for irregular executions for, let's say, unpredictable or unpredictable branches and load imbalance, which is pretty much what graph processing has to offer. So it's really data driven. In most algorithms, you have serious imbalance. This is all driven by the topology of the graph itself. You have poor data locality, and in many cases, you have very little computation to communication ratio. So in other words, well, there's been a lot of argument that this is a mismatch. Now, of course, when you tell that to parallel processing people, what do? They come up with new algorithms and new methods to do graph processing. So in fact, what that generated was a huge amount of solutions and platform-specific or system-specific ways to do graph processing such that we use the performance of existing parallel architecture. So basically, we have observed in the last 10 years at least, pretty much any conference in the field would have a few good papers about how do we rewrite or re-engineer a particular algorithm to make better use of parallelism in graph processing. What this leads to, however, is this idea or this problem that we get more and more algorithms for doing the same processing, and they remain dependent on the architecture and dependent on the graph underlying or the topology of the graph that we're using the algorithms. So where are we now? We have many parallel algorithms for graph processing, and the key challenge becomes how are we using the existing hardware or the existing systems to efficiently to get good performance without really being completely or very, very inefficient. Now, we looked at this problem a while back, and we tried to put this in a nice framework. And the idea was at the time, and that's, I think by now it's really almost 10 years, the idea was, well, let us do a very nice modeling-based approach in which we try to model the hardware, model the workload, so the application, the algorithm itself, and the data set. And then by putting them together in a very nice neat model fitting approach, we come up with what is the best algorithm and potentially hardware combination for a given workload. In other words, if I give you an input graph and I tell you I want to do some form of traversal on this graph, please tell me what is the most efficient platform that I can use for something like that, so for this particular workload. So this was really the underlying, let's say, massive research question that we had when we started this work on graph processing. So what I'm going to tell you today is a little bit on the step-by-step journey that we took trying to answer this question. And I can already put a spoiler alert here. We're not going to give an answer to this, but I'm going to show you pretty much 3 different ways in which we can go around this question and still find out very interesting results. So bear with me. I hope that by the end we'll have a bit of time to actually brainstorm about, you know, how can we move forward in this kind of grand challenge that I just highlighted. Good. So I'll talk very briefly about the why is this so complicated. Then I'm going to do a short detour towards controlled experiments. I'll explain this a little bit better. And then I'll dive into a bit of modeling, showing 2 examples, well, actually 3 examples of how we can do performance modeling and how we can use performance modeling to improve graph processing as an operation. Good. So starting with the beginning, what is really the challenge, or why is this such a complicated problem? So I'm going to give you a couple of examples, namely 2 applications, BFS and PageRank. I'm going to discuss them in a bit, but I'm going to start with a very basic, let's say, observation of the way we do parallel graph processing, looking at one of the very basic operations, namely neighbor iteration. So in principle, you will see that all systems or algorithms that we see out there are kind of broadly classified into either edge-centric or vertex-centric, namely, simply put, you have 1 thread per edge versus 1 thread per vertex. And in the case of the vertex computation, you can have a push model or a pull model. Push meaning you send your data towards your neighbors, and pull meaning you get your data from the neighbors locally. I think that's kind of intuitive if you have a bit of a, let's say, high-level understanding of parallel processing, that this leads to different amounts of work and also potential contention issues like atomic operations versus non-atomic operations. So I'm going to use this vertex-centric, edge-centric, and pull-push in the discussion further. Moreover, I'm going to give you results on a set of graphs that we collected from data sets in 2 different repositories, namely Snap and Connect. And you will see results on 9 graphs. Now, we have results on 200 plus graphs, but these are specifically selected to demonstrate the range of challenges that one can observe in practice. All the results are extracted on an NVIDIA Titan X GPU. Again, this is only a snapshot of all the results we have. The situation, or let's say the results you're going to see are representative for other systems and for other graphs as well. As I mentioned, we're going to talk very briefly about BFS. So BFS traversal, meaning we're traversing a graph by trying to touch all the reachable vertices from a particular root node, and we're traversing the graph in layers. So basically, as the graphic indicates, we go first the roots, then the neighbors of the root, then the neighbors of the neighbors of the root, and so forth. And the current level being explored is called the frontier. This will probably come in handy later on in the discussion. The challenges here, of course, there's very little computation. Load balancing could be an issue, depending on how you actually parallelize this, of course. And you have significant irregularity in the memory accesses because you're accessing this driven by the topology of the graph. So basically, the accesses are not necessarily, or they are dependent on how you store the graph in memory. Let's just leave it at that. I will show you results from 6 different versions. Again, we have experimented with up to 20 different ways of graph processing. So as I was saying, we observed at some point we had a list of 25 plus BFS algorithms that were significant, well, let's say noticeably different. And therefore, we saw this different performance behavior for many of these algorithms. But for let's say for tractability reasons, let's just keep this at a small number of such algorithms. So this is the first performance result. So horizontal axis is the index of the graph. That's not really that important. So we're just going to keep the numbers from now on. Vertical axis is normalized runtime, meaning the slowest algorithm hits 100% and the smallest bar is the fastest algorithm. And what you should observe immediately in this picture is that different algorithms are worst and probably not really very easy to see, but different algorithms are also fast, or the fastest and the slowest, depending on the input graph. And of course, we have this very large performance gap. Say, for example, here, I'm not sure if you're seeing my mouse. So, for example, here you see that the performance gap between the best and the worst can be significant in the sense of one or more orders of magnitude. So this basically leads us to observe that we do have a significant performance problem in the sense that if we're choosing for the wrong algorithm for the wrong graph, we can pay a penalty of up to, say, 2 orders of magnitude performance loss. Of course, the challenge again is to figure out which one is the algorithm that we should choose. So knowing we want to do BFS, knowing that we want to do this on a GPU, and knowing that this particular, I don't know, graph 5 is the graph we're looking at, which algorithm should we choose? This is really the key research question. This is the holy grail, if you want, of trying to find to use or to select the right algorithm for the right workload, which was our motivation all along. Now, if you're thinking, okay, but BFS is terrible as an algorithm because it has a lot of very unfortunate properties, we can also look at something like PageRank, where you have, let's say, 2 small advantages. 1, there is some computation happening, and 2, you have all the vertices being potentially active in every iteration. So you're not having this layered version, but rather this layered behavior, but you would have kind of a full graph behavior for every iteration. And again, it's an iterative algorithm. Similarly, not a lot of computation, and similarly, because we're still talking about looking at different neighbors, we get irregular memory accesses. So some of the performance problems remain active. We also have multiple versions of this algorithm implemented, and we're going to see, as you probably by now guessed, a very similar graph. Again, horizontal axis is the graph ID, vertical axis is normalized runtime, and again, pretty much the same picture. We see implementations that are very slow and implementations that are very fast, and again, different worst and best behaviors for different algorithms depending on the input graph. And again, significant performance loss in case we choose really badly the algorithm that we want to use. So again, the question here is, what is a good solution or a good strategy to actually select the right algorithm for the right workload? Okay, so the first thing that this was the state of, basically once we observed this, we started thinking about how can we actually solve this problem. And the first attempt or the first idea was, okay, maybe because what we're looking at in these figures is a very large variability because of the very large diversity of the graphs. So why don't we start by saying controlling the experiments or building some form of a set of controlled experiments where we have better understanding of the graphs we're using, and therefore use those controlled experiments to identify which graph features impact performance. Say, if we take BFS, what is the key graph feature that we can pinpoint as being the most problematic one when we talk about BFS performance, specifically about different types of BFS algorithms. So what we wanted to do, and this again is just a very brief intermezzo, because I really think this is a promising direction. What we wanted to do was to come up with a way to generate controlled graphs. Now, there are many graph generators out there, most of them much more complicated than ours. What we wanted to do was really to do a very simple operation, namely graph scaling. So we wanted to, given a graph, can we actually find out a method to scale up or scale down this graph such that we build a family of graphs on which what you would want to see is a beautiful scaling behavior that you see if the graph is half the size, then we get half the performance or half the execution time and so forth. So we were really looking for a method that will help us understand which features would be reduced in half when we say half the graph, such that we observe very good scaling behavior. So to do that, we actually came up with a very simple method of scaling graphs, namely scaling down by using sampling, and scaling up by using stitching. So what does that mean? It means we take the graph for scaling down, we take a sample of the graph based on existing sampling algorithms that are, let's say, analyzed and guaranteed to preserve certain properties. For scaling up, we generate a set of samples from the original graph, and then we stitch them together by using different interconnection strategies, different bridge vertices, so by linking these different samples or subgraphs at different points, and potentially by looking at multi-edge interconnection. So interconnecting, say, two nodes between two different samples. Say, for example, here you could have this as a single link, or this could be two different links or four different links if you want to preserve certain properties. So we've done a very nice analytical work here. We managed to explain a little bit what to expect from the performance, for the features of the resulting scaled up graphs. So we kind of were very happy to have our graph generator up and running. And then we said, okay, so now we have families of graphs. Can we actually observe nice scaling behavior? So can we find the solution, or can we find the right properties such that we observe a good scaling behavior? So the results were, let's say, lukewarm. So what you see here is a set of graphs. So each graph shows the behavior of two algorithms. Left-hand side is BFS, right-hand side is PageRank, using two seed graphs, that's less important, at different scales. So basically all the scaled versions are obtained using our scaling up method, using 3 sampling algorithms. And in this particular case, we're looking at the scaling by 2, 4, and 8. Now, what we observe is that in principle, looking for very, very far away, it looks like we have succeeded. It looks like we have managed to scale up graphs and observe very nice performance scaling behavior. In practice, however, as expected, the devil is in the details, because as we started looking into more, let's say, zooming in at different types of graphs, we started seeing significant, let's say, deviations from the performance that we expected. So we managed to scale up the graphs, we managed to control some of their properties, but we were not able to pinpoint like one-to-one a scaled graph with a scaled performance. So there's still quite some challenges, or quite some inherent variability or inherent challenges in or things that impact performance that we are not able to yet capture in this analysis. We have done more work in this direction. If you're curious, we can discuss this towards the very end. But the bottom line is, this is, I think, a promising direction for doing more analysis on the features that impact performance. But right now, I don't know, or we couldn't think of any solution that is a little bit more intelligent than trying different families of graphs, different scales, different algorithms, and basically doing like kind of like a massive set of experiments to look for, let's say, something like a bit like anomaly detection, but in this case, not anomaly, but really looking for that right mix of properties that will give us the perfect scaling behavior. So again, I think this is an interesting direction. But we did not really pursue this further because it turned out to be a very time-consuming approach. Okay, so we gave up a little bit on the idea of doing controlled experiments, or I should actually say what we've done is we kind of incorporated this opportunity of scaling graphs back into our modeling approach, and we went more into the direction of performance prediction. So again, the goal is, can we predict what is the best algorithm for a given graph on a given platform, aiming to do a particular processing. So in a nutshell, how can we choose the best algorithm? Now, the performance modeling person in me, very excited about the whole idea of performance modeling, figured, okay, this is straightforward. We're going to model the algorithm in some form of an analytical form. We're going to calibrate this particular model to the platform, be it a GPU, a CPU, or different CPUs, different GPUs, and so forth. We're going to model the data set by extracting those important features that we kind of observe have a significant role. And then we just predict the execution time as a function of these three types of elements, namely the platform, the algorithm, and the data set. Then by predicting the performance of different algorithms, we can just simply rank them and select the best one that runs, that gives us the best performance. So very, very same methodology, or methodologically speaking, perfectly fine. So we proceeded to actually develop such analytical models. So what did we do? We looked at the implementation of the different algorithms that we talked about before. So different types of edge-centric versions for both PageRank and BFS, different types of algorithms that are vertex-centric. And we started by basically saying, okay, this is a memory-bound operation, clearly, because there is no real compute. So we're going to look at trying to model, literally by counting, what is the amount of operations that are being executed, and then multiplying that with the cost of every operation, we should be able to rank algorithms by performance. So what you see here is an example of such an analysis. So in the figure on the top, you see the algorithm, kind of the pseudocode high-level implementation of PageRank using an edge-centric approach. And on the bottom side, or on the bottom, you see the performance model that we extracted. So namely, we do 4 read operations and 1 atomic operation for every edge in the system. So when we sum this all up together, this kind of generalizes nicely to basically having 4 times the number of edges in the graph's read operation plus 1 time the number of edges in the graph atomic operations. Now, I have proceeded to do a similar approximation for the other type of algorithms, and we ended up with these very neat performance models in what we thought would be very, let's say, not easy, but kind of clear parameters of the machine, namely the cost of the read, the cost of an atomic, the cost of a write, and so on. So basically, this led, as I was saying, to different algorithms for different models. So this would be an edge-centric version. This would be a push algorithm. This would be a pull algorithm. And then we decided, okay, this is a fairly simple algorithm. So we tried to kind of a very simple model. We tried to actually validate this, and we found we were significantly off in terms of the number of operations we've been doing. And of course, the reason for that, as all of you know by now, is that these were pseudocode algorithms, and then we needed to really look a little bit more at what the generated code was actually doing. So we went back to the PTX code. This was still a GPU implementation. So we went back to the PTX code and looked at the actual implementation and found out that, let's say, with a little bit of let's say pen and paper, we could extract fairly decent, accurate performance model in terms of the number of operations. So we kind of extracted these models for the different types of algorithms, and we came up with something in this form. So again, please note that all these models are basically looking at a few parameters: the number of vertices, the number of edges, and then the cost for different operations, reads, writes, and atomics of different kinds. You also see this suspicious factor of 32. This has to do with the warp size on an NVIDIA GPU and how certain operations were executed in lockstep. So what we wanted to do next was to actually extract this cost for reads, writes, and atomic operations from the different GPUs that we were running, and using the edges and the vertices as part of the graph specifications. Of course, that turned out to be a lot more complicated than anticipated, in the sense that on the one hand, the good news was the work models were correct. So these were models that were able to capture fairly accurately the amount of operations that were executed. So we could actually predict how many, with very good accuracy, how many reads, how many writes, how many atomic operations were executed, which was really good news. But it turned out that the actual calibration was much harder than anticipated. So what we were expecting was that we will be able to somehow approximate the read, the write, and the atomic with some form of cost or cost functions that were reasonably easy to extract. And it turned out that this was not feasible, or we didn't really know how to do this properly. At the end, we found out that depending on the order of execution, on the machine itself, on different ways in which basically different algorithms would lead to different numbers for a cost of a read or a write or an atomic. And that had to do, of course, with the complexity of the GPU itself. And we were not really able to capture in simplistic ways all the effects of coalescing, lockstep execution, caching, and atomic contention to the point where this cost could be accurate enough to give us a proper ranking. So I don't want to go into more detail. Again, if you have more questions, please ask. We really want to continue this work as well. So we actually took a step forward and looked a little bit into whether we can use some of the performance counters that we could extract and a lot more analysis using the, let's say, the families of graphs to extract or to give better functions or better understanding of these calibrated values. But the end result was inconclusive. So at this point in time, we wouldn't know how to extract costs that are easy to use and understand without relying on basically massive benchmarking and extracting them like that. So in the end, we kind of stopped at this point in terms of analytical models and decided that the calibration requires a significantly more detailed model of the GPU execution. And we decided to do, let's say, a little bit of a, how would I call this in a polite way? So I'm going to say a trick. So we basically said, okay, we have a lot of data from all our experiments. Can we actually extract some more knowledge from this experimental data? And then we started going more into the direction of machine learning. So again, what we were trying to do was this, but in practice, we were not able to properly predict performance. And therefore,
ja, ich hatte gerade nur schnell ein Ding laufen, aber ist noch nicht vorbeigebracht.
I think that's not a question for me.
Viele Leute, aber man kann parallel schneiden. Und dann habe ich nicht so gesagt, hier komm du links, ich rechts. Das Ding ist ja breit genug. Übereinander ist verboten, denke ich. Also da steht, dass man nicht mehrere gleichzeitig.
Okay.
Sorry about that.
No worries. I'm sorry, I did not understand that. It was something about parallel. I could hear that, but more than that. So if that was a question, then I'm happy to discuss this a little bit.
It was not.
Okay, thank you. So bottom line is we were able to model the algorithms, but we were not really able to do any proper ranking with this approach. So instead, we went to this machine learning idea, in which we build a data set of 200 plus graphs from these different repositories. And for BFS, we also looked at the different starting nodes in each one of these graphs and generated quite a large data set of input graphs. Then we measured the performance of all this data, of all these graphs using different GPUs, all these different algorithms, different implementations for BFS and for PageRank. So we have a massive database that has collected all this information. And eventually we started looking at data-driven or machine learning models using this performance data. And our first attempts were actually still kind of hung on the idea that we want to predict execution time. So we tried, based on previous work in our group, we tried to do an execution time predictor using random forest. And that turned out to be quite good for PageRank, but still not going very well for BFS. We then kind of dropped the idea of trying to predict execution time, because again, the idea was we predict execution time, we rank based on execution time and pick a winner. And we figured maybe with a machine learning approach, we can just pick the winner directly without going to attempt to predict execution time, but rather trying to predict the best execution time directly. So predict a ranking. In this case, we use decision trees based on different graph features. And again, this went well for PageRank with high accuracy, with relatively low prediction costs, but still not working for BFS. So at this point, we were starting really thinking, okay, what is going on here? And then we eventually looked a little bit in more detail at the data that we see for every input graph for BFS. So at this point in time in this graph, what we see on the horizontal axis is the level in BFS, and vertical axis is runtime not normalized. So smaller is better or lower is better. And what we observe is that for different levels in the same BFS on the graph, we have different algorithms winning. So again, in level 1, we can have an edge list. So it's not an edge list. I think this is one of these vertex push that is very fast. But as we go further, it turns out that the edge burst could be very fast. So at different levels of the BFS, we are observing different algorithms being the best performing ones. So in fact, trying to predict an overall winner was simply too complicated for the approach we took. Instead, what we had to do was actually trying to predict the performance at every level, and then based on that, combine or reason about what would be the overall performance of the BFS algorithm. So at this point in time, we were not able to find out what is the best algorithm for a given graph. We could not really find out an easy way to kind of combine, but I should say it like this, but at every level, we could predict what would be the best algorithm for that level. So that doesn't still mean that we can select the best possible algorithm at overall for the entire graph, but instead it means we can actually construct the best possible algorithm. So instead of saying we're going to try to guess what is the best overall algorithm for a given graph, we shall construct that by modeling at every level what is the best possible. By determining at every level what is the best algorithm, and then by stitching together these different levels in every iteration. So say for level 1, it could be edge, level 2 could be edge, level 3 could be vertex, vertex, edge, vertex, vertex, vertex. And that would be kind of then we know that is going to be the best algorithm by construction. So we can't predict what would be a non-changing algorithm, but we can construct a changing algorithm per level that could build us the best possible BFS for a given input graph. So basically what you see in this graph is that this optimal constructed version, which is this stitching of the best at every level, at this point in time with Oracle predictions on knowing based on measurements what is the best version, is pretty much winning at all times. The only times when it's not winning is when there is no change. So the same algorithm stays the best in the full graph. And then the fact that you're stitching things up would give you some overhead. So that's the only situation in which this kind of mix and match algorithm, as we call it, will not win. So in a nutshell, we were able to construct the best algorithm by predicting ranking at every level, and then mixing and then switching the algorithm on the fly for every level, depending on the prediction of our model. And this was this idea of mix and match that I just discussed. So how do we do this in practice? I can skip this. Basically, the whole idea is based on the data that we have collected. We're building a data set for training. We're training a very simple model based on decision trees. And then we apply this at runtime for this particular selection. On top of that, the training procedure can also give us some understanding of feature importance, which we are still trying to exploit to kind of go back a little bit to the analytical model and see whether we can capture this idea of what graph features would be significant for performance. Now, of course, the question is, does it really work in practice? So we have implemented this in our mix and match BFS type of algorithm, and we compare this against alternatives or alternative systems. Horizontal axis this time is the graph from the table in the beginning, so one of the 9 graphs that we discussed before. Vertical axis is again normalized runtime, and what you see with yellow is our version really measured based on this predictive switching at runtime. So all these, in all cases, we are we're performing quite well. Let's say the only one that is beating us is this optimal algorithm, which is basically the switching without the overhead of predicting. So we're not, this optimal is kind of post-process or done after we know exactly what is the best algorithm. So there is no overhead for prediction. We're simply having a list of what every level has to do, and we're running that without any overhead for the prediction. So basically what we learned was that we were able to switch at runtime. We were able to use this approach of modeling to actually predict correctly in most cases, and we were able to significantly outperform existing alternatives where there was no switching of algorithm at runtime. So I do have one small part about a strongly connected component, but maybe in the interest of discussion, I can stop here for a couple of minutes if there are any urgent questions. So let's take a time for questions before I briefly present the last part.
All right, are there any questions? You can just speak up or raise your hand. I have a question about your workflow slide. Like 2 slides ago, I think, where you say right here, feature importance, which is promising from making sense of results. So could you say something more about that? In which way do you use the insight, or do you extract insight about feature importance?
So at this point, we're not using that at all, but we found out things like by looking at for example, the features that we're using here are the number of vertices, the number of edges, the size of the frontier at every level, and the amount of graph that has been already visited. So we could, basically this analysis tells us which one of these features would have more importance than the others, or it will kind of rank them in terms of their relative importance for our model. We didn't look into this in enough detail for me to be able to say exactly what is the ranking for these features, but we did find out that indeed the size of the frontier, again, these are kind of intuitive things if you start thinking about it from the perspective of the algorithm, but that the size of the frontier is more important than the amount of edges that the graph would have, especially for vertex-centric algorithms. So it would be this type of information that would maybe help us improve or think a little bit more on how we want to improve our analytical models.
Okay. Any more questions or comments about this part? Okay, then just let's go on.
Okay, so I only have a few slides about a different algorithm that we looked at more recently. So everything we discussed so far was more about this idea of neighbor iteration and looking at algorithms like BFS and PageRank, where we know for a fact that there are topology, again, intrinsic topology features that will lead to performance variability, to significant performance variability. So we wanted to try to apply a similar approach for a more complicated algorithm. And for that, we looked at strongly connected components. So effectively, the idea here was, can we somehow find what would be a good SCC algorithm, or predict somehow the performance of strongly connected components on a given graph. And to do that, we looked at an algorithm called forward-backward, which is basically a recursive algorithm that splits the graph into different parts and eventually, again, recursively splits the graph up to the point where it finishes splitting it up in connected components. Let's just put it like this very simply. So this is really the, let's say, the most common parallel algorithm for strongly connected components. It exists for many years by now. And one of the optimizations that has been added to this algorithm is to solve this problem of trivial components, namely single vertex components that kind of slow down the breaking up of the graph. So if you keep, say if you have a very large graph and you keep breaking it into very small trivial components, the process, the process takes very long, because instead of really splitting this in a more kind of balanced way, you keep splitting it into trivial components. So this is a performance problem for such an algorithm. So effectively, the solution for this is to do this trimming step, in which you remove these floating vertices before you do the algorithm. Or let's say at particular moments in time, you check the graph whether there are such floating components, and you eventually remove them. So this is a separate step of the algorithm and is seen as an optimization. Of course, the problem is the mix of the two things, this forward-backward algorithm with trimming, is significantly impacted by the graph topology. So depending on different graph topologies would lead to better or worse success of the trimming algorithm, to the point where the trimming itself can become overhead. So actually adding trimming of graphs that have very few trivial components is something that will give you performance degradation rather than performance improvement. So the question that we had here was effectively, can we come up with some form of a model that would predict when to trim our, so when in the process of applying the forward-backward algorithm, we should be trimming for these trivial components. So based on the literature and based on our own observations on kind of an empirical analysis of performance, we have found out there are 4 different ways of let's say, statically trimming. So what do we mean by this? It means we do not take the topology into account in any way, but simply we have 4 different strategies. We never trim. We always trim before we apply the forward-backward. We look for trivial components. We trim them out. We trim once in the beginning, or we trim once after the first iteration. So this gives different versions of, let's say, trimming strategies, and of course, as you probably expect, this will give different performance depending on the input graphs. Now, this time, this is a CPU implementation. We looked again at a very large set of graphs with different dimensions. Please note that these graphs are significantly smaller than in the previous case, and we can discuss about this later if you're interested or curious about why this happens. And then we started looking at, okay, which one of these 4 strategies is going to give us the best performance? I'm going to skip this a little bit, and I'll show you a few results. So this is again for the static models. What we see here is for the different strategies, the total number of graphs and the count of the cases in which this particular trimming strategy, namely never, always, initial or no initial, wins, loses, and it kind of gets stuck in the middle. So again, what you observe, pretty much like in the previous discussion, different graphs would fit different strategies for trimming. Also, there will be a very little let's say, a ranking difference between these different versions. So this is an average ranking over the entire set of graphs, and you see that none of this is really a particularly, let's say, a clear winner in terms of which one is best over the entire set of graphs. So again, the same story, depending on the graph topology, one of these strategies is best, but we don't know a priori which one. So then we also looked at the average execution time, so we can skip this. This is pretty much the same story looking at different metrics. And the solution we found kind of inspired a little bit by the previous approach was to actually add this very small AI-based model that will give us a prediction of whether we should or should not trim. So what we do is we basically put literally tiny neural network here that is trained to predict whether in this particular moment of the algorithm we should trim or we should not trim. And then we apply the trimming according to the model, and then we see whether the performance that we obtain with this particular model is better. I can skip a little bit about the actual training of the network, and then we can look a little bit at the performance. So again, same type of graph, different types of trimming. And what we see here, interestingly, is that the AI implementation is actually also one of the many. It actually wins in very few cases and loses in a significant number of cases. So it is not, let's say, outperforming everything and at every time. And also in terms of the overall ranking, we see that the AI is kind of a very mediocre at best. So we're not really seeming to get overall a crashing success with our AI-based approach. However, when we're looking a little bit at the average execution time, we find that actually the AI version is the one that gives, on average, the best performance. And in fact, it is really the one that gives the, let's say, the least penalty on average across the entire set of graphs. So, in other words, what the AI-based version is doing is to give us a more stable execution. So it doesn't give us a winner per se, but it gives us the ability to take the topology into account and to, let's say, improve the overall impact of trimming. It is not best because trimming in itself, so the prediction and the case in which the prediction is wrong, are quite a significant overhead overall. So in practice, the current implementation is not very efficient for the trimming and prediction part itself. So in other words, what this approach gave us is literally a way to take the topology into account and on average get a better or a more accurate selection of trimming based on the graph topology. That doesn't mean that it is always the best algorithm, but that it is on average the one that gives us the best performance for a large diversity of graphs. So this kind of brings me to the conclusion. So I showed you a little bit of our work on parallel graph processing. I showed you a little bit of different approaches to modeling, including this idea of building graph generators to help us extract the particular elements of graphs that will give us a performance or that will impact specifically the performance of different algorithms. And I want to point out that I think what we've learned in this kind of 8+ years of graph processing or parallel graph processing is that the performance of these algorithms really depends non-trivially on platform, algorithm, and data set. And we see a lot of work happening in building algorithms for specific platforms, typically taking the data set as a type of data set into account. But in this case, these algorithms are not portable. GPU algorithms don't work well on CPUs, and obviously vice versa. We also see that there are specific developments in algorithms for specific types of data sets, so say for social networks or for road networks or for logistics. We already see that we have different algorithms to calculate different things. But again, these are not portable between different types of graphs. And in general, this kind of correlation between what is a good data set for CPU execution versus GPU execution and whatnot is something that is not very well understood. So there's quite a lot of, let's say, generalizability work to be done here. But right now, it seems we're still looking into pairs of these three things and not really tackling the whole thing altogether. And in terms of specific, I showed you a little bit about our graph scaling tool, talked about mix and match and how we can create the best algorithm for BFS traversal by design. And I showed you a little bit about FBTrim and how we use a very small neural network to make decisions on the fly about trimming or not trimming in strongly connected components. With that, thank you very much for listening, and I hope there are some questions or discussion points.
Thanks a lot, Anna, for this very interesting talk. All right, so are there any questions or comments? Just speak up. Don't be shy. So I have a general question about parameterizing graph topologies, which you would somehow need for doing the analytical approach for things like PageRank and BFS. How can we, or what kind of directions did you follow when parameterizing the topology of a graph? I mean, they're very simple metrics, but there might also be more involved non-intuitive metrics that you could use. So how far have you gotten there?
I think that's a very good question. So I think in terms of practical things, we've gotten as far as looking at sizes, so number of vertices, number of edges, degree distributions and different ways of expressing degree distributions. This idea for BFS, we really found out that it's super important to know the size of the frontier at every level, which is in itself a discussion point on So that in itself is a challenge. We did investigate in our graph scaling work, we did investigate different types of properties. So we looked at what are people measuring about graphs. And I think we came up with a list of about 25 different properties that are relevant for different graph algorithms. But we could not find any mapping from properties to graph algorithms performance. So we never really got to the point where to say with very clear analytical reasoning, this particular property impacts this particular algorithm in this particular way. So we've done some work with the graph sampler where we really did a few iterations of scaling up graphs by changing different properties and seeing, okay, if we change the graph in this way, the performance changes in this way. Or if we change the graph in this other way, the performance is not affected. So we have some iterations like this, but nothing systematic enough to say we can come up with a more detailed model than something like, as I said, degree distribution size, and for the case of the BFS, the frontier size. So I would say right now it's rudimentary, and I'm not really aware of a lot of work that has gone much further than that. But I'm not really familiar with the, let's say, I'm not familiar enough with the mathematical side of the story.
Okay. When you refer to, or the thing you said at the beginning about graph scaling and how it didn't quite turn out as expected, only from a very high bird's eye point of view, I imagine that in this graph scaling business, you want to aim at some kind of steady state where if you double the size of the graph, nothing substantial, whatever that means, changes if you do that. Of course, it's evident that if you make it too small, then you have certain effects like bad occupancy, very high cache reuse. If you make it too large, then it becomes very much latency bound. So there's an area in between where maybe you have some kind of steady state where nothing substantial changes as you double a certain number of times. Is that what happens? Is that what you observe?
Yes, so this is exactly what happens. So I think this is pretty much what I would hope we will have some, let's say, time/money/students to actually investigate further. That's what I meant when I said, well, we're still kind of finding what are the bounds of this part of the space that is interesting. We definitely have seen interesting evidence that we can identify such regions for different graphs. The only problem is for different machines, so for different types of GPUs and CPUs, and for different types of graphs, that region shifts. So I wouldn't know how to do this in other way than like a massive for loop inside another massive for loop inside another massive for loop, where we try pretty much every option to find out where this kind of range is and what are these different properties that we can that we can vary one at a time, because that was the idea. The idea was, can we vary properties one at a time and see how they behave? So what happens to performance? And then again, hoping that if we scale this one and then performance goes like this, then we found a correlation. So I wouldn't know how to look for that correlation other than through massive empirical experiments. But I'm happy to collaborate if anybody has other ideas.
Talking about performance, as you know, in our group, we very much focus on resource-based performance modeling, and we try to find a spot when optimizing a certain algorithm where we're sort of bound by a bottleneck. Now, you didn't talk about whether or not these graph algorithms actually address any of the bottlenecks we have on the hardware, like in the GPU. So I could imagine that whatever you do, unless you're in a very benign corner of the configuration space, you will not actually utilize the capabilities of a GPU to its full extent. So neither the bandwidth nor the occupancy. So it will be more or less a lukewarm utilization of all resources. That's correct?
Yes, I think that depends a little bit on the algorithm. So if you do edge-based algorithms, those would be quite decent on occupancy, but and load balancing, because this would be super balanced. But you will start seeing massive problems due to atomics, because you have different numbers of neighbors, and then you have different contagion at pretty much every vertex, and therefore you will have very nice load balancing up to the point where you need to do atomics. So that one will have a decent occupancy, but for let's say most of the execution, but then the atomics are going to be the ones that are going to kill all the fun. For vertex-based, you're right. This is pretty much yeah, neither here nor there. So the GPUs are not massively utilized in any way, or not really bottlenecked specifically by one thing.
Okay. There's a question from Christian. Did you explore parallel probabilistic graph algorithms?
Oh, that's a very nice question. So no, we ourselves did not. I have seen, let's say, interesting developments in that direction. We did not look into that, but I think that's definitely quite some interesting approaches coming out of that field, let's call it. So we didn't look into that at all, really.
Okay. More questions or comments? Almost out of time anyway. So let me thank you again for the very interesting talk.
Thank you very much.
And hope to see you again soon, maybe in person. SC22 is drawing near.
Yes.
So let's see how that works out.
Sounds good. If anybody has any further questions, my email address is available, and I'm more than happy to discuss this. And if you have ideas to collaborate and all that, again, feel free to reach out. I'm still very much interested in this type of work. So I think there's really quite a lot of fun stuff to learn about graphs. So reach out if you come up with any kind of last minute burning question or whatnot. And okay. Thanks again for having me and for listening to me.
Thank you for being here. Thank you for everybody. Thank you to everybody who attended, and goodbye. See you next time.